Well, today's task is to evaluate compound inequalities. And we've got to graph these and state the solutions in set builder notation and in interval notation. So let's start with this compound inequality. Negative 9 is less than or equal to 5x plus 11, which is less than 21. So our first task, by the way, we have three intervals here, 1, 2, 3. Our first task is to isolate the term with the variable in it and then isolate the variable between the inequality symbols. So let's get rid of this 11, so we have 5x isolated between our inequalities. To do that, we'll subtract 11 from each interval. So minus 9 minus 11 is a minus 20. And 21 minus 11 is 10. Next step, we must get rid of that 5. So to do that, we'll divide each interval by 5. And negative 20 divided by 5 is negative 4. 10 divided by 5 is 2. So there's our solution. And the graph, we'll put a hash mark at negative 4. Another hash mark at 2, x is the variable. Now, because an equal sign is associated with this inequality, we'll put a bracket at the lower bound 4, no equal signs associated with the upper bound 2, and we'll shade everything in between. So there's the graph. In set builder notation, the solution is x such that negative 4 is less than or equal to x, which is less than 2. And in interval notation, we have negative 4, a bracket, and 2, and a parenthesis. Well, for number 2, we have a compound inequality. And we have to satisfy both of these. The word "and" says we have to find an x that satisfies this inequality and this inequality. So let's start simplifying. So for this, we have to isolate the 3x. We'll do that by adding 2 to each interval, and 2 plus 4 is 6. And 5x, and we'll subtract 7 from each interval, and we get 32 minus 7 is 25. Now dividing through by 3, we have x is less than or equal to 2, and let's see, dividing through by 5x is less than or equal to 25 divided by 5 is 5. Now let's graph each of these. For the one on the left, we have a hash mark at 2. There's an equal sign associated, so we'll install a bracket at that upper bound and graph everything to the left. For the inequality on the right, we'll put a hash mark at 5, a bracket, because there's an equal sign associated with the inequality, and shade everything to the left. Now, we need a set of values that satisfy this inequality and that. And notice, any value greater than 2 but less than 5 will fail to satisfy this inequality. So our solutions are going to begin at 2 and go to the left. So we'll graph that set of solutions. And here they are, 2 to negative infinity. So in set builder notation, we have the set x such that x is less than or equal to 2. In interval notation, we have negative infinity, parenthesis, 2, bracket. For our third compound inequality, we have negative 4x minus 3 is greater than 1, and negative 4x minus 3 is less than negative 5. So, starting at the left, we have to isolate the term with x in it, then we'll isolate x. So adding 3 to each interval, we get negative 4x is greater than, and 1 plus 3 is 4, and adding 3 to each interval, we have negative 4x is less than, and 3 plus a negative 5 is a negative 2. Now, in order to isolate x, we'll divide by a negative 4. When we do that, and when we multiply through or divide through an inequality by a negative, we have to flip the inequality. And 4 divided by negative 4 is negative 1, and now we'll divide through by negative 4 to isolate x, and we have to flip the inequality then, and negative 2 divided by negative 4 is 1/2. I think we can graph each of these on the same number line. So here we are at negative 1, and there's no equal sign associated with this inequality, so we'll put a parenthesis and shade everything to the left. Add a hash mark at 1/2. Again, no equal sign associated with the inequality, so we'll put a parenthesis and graph everything to the right. Now notice, the word "and" means we want all values that are in this interval and in this interval. There are none. Either you're to the left of negative 1 or you're to the right of 1/2. There is no value that can be in both intervals at the same time. So the consequences are there is no solution. If we wanted to write a set builder notation and state that, we could say that x such that x equals the empty set, but I think no solution will do.